Good morning, everybody. So this week we have been researching the abundance patterns of intertidal organisms. I'm Caitlin.
My name is Daniel.
I'm Vanessa.
Carolina.
And our mentor is Lindsay Peavy, and our PI is Steve Gates.
Exactly 2 months ago, there was an oil spill not too far from here, and it raised many concerns. The crude oil that spilled into the ocean has many added chemicals that can have a disturbance on marine life. This is a map of our coast, and we are currently situated here at UCSB. The oil spill happened at Refugio Beach, and pink shows the estimated area where the oil spread. And as you guys can see, it has covered a large part of our coast. However, we're just focusing on the intertidal organisms at Full Oil Point, being that for a group of researchers have gathered data for a couple of years now. So it gives us solid baseline data to compare our post-oil spill data to see whether or not the oil spill had an effect on the organisms studied.
So our main objective is to compare the population counts of intertidal organisms before and after the oil spill. And currently, many researchers are conducting their own oil impact studies, and our data that we collect will be useful to these organizations.
So some of the organisms that we have studied is the sea lettuce, which is this green algae in the background, that sea star, which is held in his hand, the owl limpet, which is a mollusk that looks kind of like a rock, the large anemone, sea mussels that people commonly eat, and hermit crabs that people also have as pets sometimes. So the owl limpet for us was very important because it is sensitive to the toxic chemicals in the environment. So it's a great indicator for how severe the oil spill really was. And so if the population of the owl limpets severely dropped, we could correlate that with the oil spill. It's also good because it reacts fastly to the toxic chemicals instead of dolphins who react a lot slower.
Sea stars over here are equally important to our research due to the fact that they are considered keystone species. And what does this mean? It basically means that their disappearance could signify a loss in the balance of the whole ecosystem.
So our null hypothesis is that the oil spill has no effect on the population count of owl limpets, hermit crabs, large anemones, or sea stars. And if we find this to not be true, we'll be forced to reject the null hypothesis and accept the alternative, which says that it does have an effect. To test this, we have two methods. First, the 100-meter sweep, where we will count the sea stars and owl limpets, and second, do a vertical transect, which consists of counting the hermit crabs and sea anemones and estimating percent coverages of the sea lettuce and sea mussels. We first replicated the 100-meter sweep parallel to the beach, and so this consists of us looking in the cracks and crevices of the rocky intertidal right here. And so we start from the low tide, which is over here, and go downward to the high tide. And with this, we're able to determine if there are any abundance changes in these organisms.
Second method that we used was the vertical transect method. So basically we had a 50-meter long transect tape that went from the high tide to the low tide. And every 5 meters we would put down this quadrat, this instrument right here, and we would put the quadrat down, and every 5 meters that's where we would collect data.
Okay, so each quadrant is composed of 25 equally spaced squares, which account for about 4% of the total area of the quadrant. And how do we use this tool? Basically, we have two different approaches to it. In the first approach, we simply count the number of specimens contained in the total area of the quadrant. So for example, as we can see in the illustration over here, we have a total of 5 dots. And even though one of them is in the same square, we still count it as 5. So we get a total number of specimens as a result. And the next approach, we look at each one of the squares individually, and we tell whether or not the organism is in there. So for example, let's say that specific organisms inhabited 5 total squares. We multiply the 4% times 5, and in this case we have 20%, and this yields percent covered.
This graph summarizes some of the data we collected. On the x-axis, we have the organisms, which we counted for the large anemones, hermit crabs, sea stars, and owl limpets. And on the y-axis, we have the count. The blue is the data previously recorded, and the green is the data we collected after the oil spill. All of the organisms, we saw a decrease with the exception of the hermit crab. We actually saw an increase. And one of the reasons why that might have happened is that when there's a disturbance in an ecosystem, some organisms suffer while others thrive.
Okay, so right away you can tell that we have a lot more data for sea stars, and the reason being is that they were once really common in our coast, but after November of 2013, a disease called the sea star wasting disease successfully cleared them from our coast. On the x-axis we have the specific dates in which the surveying was conducted, and on the y-axis we have the count or total number of specimens. And again, we're beginning to see recruits or baby stars weeks previous to the oil spill. And after the oil spill, we again see a decrease in the population size, but the number is not really significant. It's just a difference of one. And we don't know whether that difference can be attributed to the oil spill or to the sea star wasting disease.
So because we did see a change in abundance count, we're forced to reject our null hypothesis and accept our alternative, with the exception of sea stars, because just as Daniel said, the population count is so small that we can't really draw any conclusions to why they have disappeared.
So the second method that we used was the percent cover, and on the sea lettuce and the sea mussels. So the method we used was through multiple linear regression, which basically is you can take multiple variables into account for one specific data, which is our percent cover. So the percent cover is determined by the y-intercept plus the x1, which is the date, plus x2, which is the temperature, plus our error. So for our x values, it's kind of similar to the y equals mx plus b equation, but instead of having just one x, we have two. The error is important because we need to account that even though the oil spill has been, it's prevalent right now, there is other reasons that this could have happened. And so, for an example, the percent cover of sea mussels that we did in our quadrat 25, is we had the y-intercept of 613 minus the 0.2 date minus 4 temperature plus the error. So our R-squared value is also 0.45. So if our model were to be absolutely perfect, the R-squared value would be 1. And since our R-squared value is so low, the coefficients of our variables, we cannot trust the magnitude of them. So instead of looking at the actual numerical value, we're looking at the direction, which is they're both negative. So since the date has a negative value in front of it, we can correlate that as the date increases, which as time goes on, the percent cover is decreasing. And same as temperature, as temperature is increasing, the percent cover is also going down. Next, we will summarize all of the specimens throughout all methods, but just for the oil spill.
Okay, so in summary, we continue to see a decreasing number of the population of different species like the sea lettuce, the sea mussels, owl limpets, and large anemones, with the exception of the hermit crab. And as Carolina already mentioned, an explanation for this can be found due to the fact that when there is disturbance in an environment, some organisms suffer the consequence while others thrive. And the sea star, well, the information in regards to the sea star is really inconclusive due to the fact that there's just multiple amount of variables that need to be accounted for. So this calls for further research.
Our research is a great impact because we were the first team to go out and collect data after the oil spill. So because we did see a difference, it motivates further research to see the long and short-term effects that the oil spill might have on the organisms. Also, our data is important to some organizations, including the National Marine Sanctuary, as well as Cole Oil Point Natural Reserve, and researchers at UCSB. Also, maybe the oil company is also interested on the effects the oil spill has.
And lastly, we would like to acknowledge our mentor, Lindsay Peavy, for guiding us through our research, as well as our PI, Steve Gaines. We'd secondly like to thank the National Marine Sanctuary, specifically Jesse Altstadt, for really exposing us to real field work. And lastly, the Jack Kent Cooke Foundation for furthering our knowledge in the science community. Thank you, and we'll be going to take any questions.